Wigner Seitz cell. The Wigner Seitz cell around a lattice point is defined as the locus of points in space that are closer to that lattice point than to any of the other lattice points. The volume enclosed is called as a Wigner Seitz method. A simple way to find the primitive cell, which is called Wigner Seitz cell, can be done as follows. Choose a lattice point. Draw lines to connect these lattice point to its neighbors. At the midpoint and normal to these lines, draw new lines. The volume enclosed is called as a Wigner Seitz cell. Crystal structure. 2. Square lattice. Centered rectangular lattice. Wigner Seitz cells. Different kinds of cells. Unit cell. A unit cell is a spatial arrangement of atoms which is tiled in three-dimensional space to describe the crystal. Primitive unit cell. For each crystal structure there is a conventional unit cell, usually chosen to make the resulting lattice as symmetric as possible. However, the conventional unit cell is not always the smallest possible choice. A primitive unit cell of a particular crystal structure is the smallest possible unit cell one can construct such that, when tiled, it completely fills space. Wigner Seitz cell. A Wigner Seitz cell is a particular kind of primitive cell, which has the same symmetry as the lattice. Wigner Seitz cell, 3D. Crystal structure. 5. Lattice Seitz and cubic unit cell. Crystal structure. 6. Fundamental properties of solids. Lecture 03. Crystallographic points, directions, planes and the Miller system of indices. Fundamental properties of solids. Crystal directions. We choose one lattice point on the line as an origin. Say the point O choice of origin is completely arbitrary, since every lattice point is identical. Then we choose the lattice vector joining O to any point on the line, say point T. This vector can be written as R equals N1A plus N2B plus nec. To distinguish a lattice direction from a lattice point, the triple is enclosed in square brackets, is used. N1, N2, N3. N1, N2, N3 is the smallest integer of the same relative ratios. Figure shows 111, direction. Crystal structure. 8. Examples 210 x equals half, y equals half, z equals 1, x equals 1, y equals half, z equals 0. Half half 1, 1 1 2. X equals 1, y equals half, z equals 0. 1 1/2 0, 2 1 0. Crystal structure. 9. Negative directions. When we write the direction, n1, n2, n3, depend on the origin, negative directions can be written as R equals N1A plus N2B plus nec. Direction must be smallest integers. Origin, O. Y direction. X direction. X direction. Z direction. Z direction. Y direction. Crystal structure. 10. Examples of crystal directions. X equals 1, y equals 0, z equals 0, 1 0 0. X equals -1, y equals -1, z equals 0, 110. Crystal structure. 11. Examples: we can move vector to the origin. X equals 1, y equals 1, z equals -1/6. -1 1 -1/6, 6 6 1. Crystal structure. 12. When dealing with crystalline materials, it is often necessary to specify a particular point within a unit cell, a particular direction or a particular plane of atoms. Planes are important in crystals because if bonding is weak between a set of parallel planes, then brittle shear fracture may occur along these planes. Therefore, it is necessary to be able to specify individual crystal planes and in the case of shear to specify directions within these planes. Such identification is carried out by means of Miller indices. Crystallographic directions. A crystallographic direction is defined as a line between 2 points, a vector. 1. A vector of convenient length is positioned such that it passes through the origin of the coordinate system. Any vector can be translated throughout the crystal lattice, if parallelism is maintained. 2. The length of the vector projection on each of the 3 axes is determined in terms of the unit cell dimensions A, B, and C. 3. These 3 numbers are multiplied or divided by a common factor to reduce them to the smallest integer values. 4. The tree indices are enclosed in brackets as UV. The U, V, and W integers correspond to the reduced projections along X, Y, and Z axes respectively. Vector A, 1/A, 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 111, vector B, 110. Z, X, Y, A, B, C, A, vector A, 1/A, 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 111, vector B, 110, vector C, 111. For some crystal structures, several non-parallel directions with different indices are actually equivalent. The spacing of atoms along each direction is the same. For example, in cubic crystals, all the directions represented by the following indices are equivalent. As a convenience, equivalent directions are grouped into a family which are grouped in angle brackets. Sometimes the angle between 2 directions may be necessary. A, H1K1L1, and B, H2K2L2, the angle between them is A. B equals vertical bar A vertical bar B vertical bar cos A. Cos A equals H12 plus K12 plus L12, H22 plus K22 plus L22. H1 H2 plus K1 K2 plus L1 L2. Crystal planes. Within a crystal lattice it is possible to identify sets of equally spaced parallel planes. These are called lattice planes. In the figure, density of lattice points on each plane of a set is the same and all lattice points are contained on each set of planes. B, A, B, A. The set of planes in 2D lattice. Crystal structure. 18. Crystallographic planes. The orientations of planes for a crystal structure are represented in a similar manner. In all but the hexagonal crystal system, crystallographic planes are specified by 3 Miller indices as HKL. Any 2 parallel planes are equivalent and have identical indices. The following procedure is employed in the determining the H, K, and L index numbers of a plane. If the plane passes through the selected origin, either another parallel plane must be constructed within the unit cell by an appropriate translation, or a new origin must be established at the corner of another unit cell. 2. At this point the crystallographic plane either intersects or parallels each of the 3 axes. The length of the planar intercept for each axis is determined in terms of the lattice parameters A, B, and C. 3. The reciprocals of these numbers are taken. 4. If necessary, these 3 numbers are changed to the set of smallest integers by multiplication or division by a common factor. 5. The integer indices are enclosed within parentheses as HKL. 1. The plane passes through the selected origin O. 1. The plane passes through the selected origin O, therefore, a new origin must be selected at the corner of an adjacent unit cell. Example, faces of a cubic unit cell. Various non-parallel planes may have similarities, crystallographically equivalent. Such planes are referred to as family of planes and are designated as HKL. Example, faces of a cubic unit cell. 100, 010, 001, 100, 010, 001, Xi, 100. Indices of planes, cubic crystal. Linear density. When planes slip over each other, Slip takes place in the direction of closest packing of atoms on the planes. The linear density of a crystal direction, HKL, is determined as delta HKL equals length hash of atoms. FCC, linear density 3.5 nanometers at 2 LD equals linear density of atoms LD equals number of atoms. Unit length of direction vector. A 110. X, linear density of Ln, 110, direction A equals 0.405 nanometers. Hash atoms. Length 1. 3.5 nanometers. A 2. LD dash equals adapted from Figure 3.1a. Callister rate Vish 8e. 26. BCC, linear density. Calculate the linear density for the following directions in terms of R. 100. 110. 111. Planar density of 100, iron. Solution. At T less than 912 degrees Celsius, iron has the BCC structure. 2D repeat unit. R. 3. 4. A. Equals 100. Radius of iron R equals 0.1241 nanometers. Adapted from Figure 3.2c, Callister rate Vish 8e. Equals. Planar density equals A. 2. 1. Atoms. 2D repeat unit. NM2. 12.1. M2. Equals 1.2 by 1019. R. 3. 4. Area. 28. P 3.55, A, planar density for BCC. Derive the planar density expressions for BCC, 100, and 110, planes in terms of the atomic radius R. Planar density of BCC, 111, iron. Solution, Count, 111, plane. 1 atom in plane/unit surface cell. 2. A. Atoms in plane. Atoms above plane. Atoms below plane. 2D repeat unit. 3. H. Equals A. 2. 3. 2. R. 16. 4. A. Area. Equals O. C cedula. E. Ash. 1. Equals NM2. Atoms. 7.0. M2. 0.70 by 1019. 3. 2. R. 16. Planar density equals 2D repeat unit. Area. 30. P 3.54, A, FCC. Derive planar density expressions for FCC, 100, 110, and 111, planes.